Hey YouTube, what's up? Dr. T here in St. Petersburg, Florida. I don't know about you, but what's up with the late release of NVIDIA's next generation Volta GPU for general purpose use, i.e. gaming? So, in case you're wondering and don't know, what is a GPU and why is it so special compared to a CPU? Here, a nice one-stop tour through the evolution of GPUs. And you're looking at a drone flying inland from the pier to central St. Pete, downtown St. Pete. This is downtown St. Pete in all its glory with all the boats and the harbour. And this is one of the central drags that goes through the centre of town.
In this video, we'll be discussing the rise of GPU computing. While CPUs utilize multiple cores and as of recently have been increasing core counts, graphics processing units, GPUs, essentially take the concept of parallelization and expand on it in a massive way. Observing the trend from the mid-1990s, you can see core counts are steadily increasing for about a decade, from 1 core in 1995 to 24 cores by 2006, so a steady rate of growth of about 2 cores per year. 2006 was an inflection point in GPU computing, where we saw a massive jump from 24 cores to over 5 times that, 128 by 2009. Progressing to present day, you can see that the shift in massive parallelism has been focused on more and more, from a rate of growth of about 2 cores per year to now about 200. As of this year, 2018, we are now reaching graphics architectures such as NVIDIA's Volta with core counts over 5,000. To understand why GPUs are becoming so widely adopted today, it is best to first understand their original purpose, graphics, more specifically for gaming. I'm sure that's how the majority of people, myself included, still view companies such as NVIDIA and AMD today. Gaming is an extremely computationally intensive task, and as the years have progressed, it has only continued to grow more and more complicated. There are so many things to simulate, such as materials, lighting, shadows, physics of different materials and their interactions with lighting as well as other materials, various fluid simulations, procedural generation, the list can go on and on. To highlight the level of complexity some games can reach, I want to play a clip from one of the most ambitious games in development today, Star Citizen. As you can see, and from the thousands of other applications I didn't even mention, games require in the order of millions, even billions of computations per second, and this is only set to increase as technologies such as VR start gaining more traction. This is why GPUs are focused and have increased so rapidly in parallelism since the mid-2000s. This massive parallelism is now bleeding into other applications. One of the most mainstream currently and why such mass adoption of GPUs has grown is artificial intelligence, more specifically deep learning. We'll explore this topic much deeper in this channel's AI video series, but essentially machine learning models typically require billions, even trillions of matrix operations, which are just simple multiplies and additions. GPUs by default excel at doing large amounts of repetitive calculations due to their use in gaming, thus deep learning was a perfect fit. All of this is a positive feedback loop. Increasing graphics and simulations and increased AI performance will propel each other forward, such as AI and computer characters and increased realism in simulations and physics. This also translates to progressing scientific innovation as well, both in the micro and macro scale, with the use of GPUs to model and research the smallest things such as protein folding to things as large as more accurate weather simulations, or even larger such as gravitational wave simulations. Now a word from NVIDIA CEO and co-founder Jensen Huang to highlight some of what I've talked about further.
In order to train this neural net with huge amounts of data, you need to do huge amounts of computation. Trillions and trillions and trillions of operations necessary to effectively, for this neural network brain, to learn how to perform an intelligent task, like image recognition or voice recognition. Well, that handicap was overcome with the discovery of the GPU. And so these two factors, the end of Moore's law and the emergence of a new software development method, a new software technique, happened almost exactly the same time. And these two dynamics turbocharged the adoption of GPU computing. This form of computing we've been working on for literally a decade and a half. In fact, you could say that ever since the founding of our company, we've focused on only this form of computing. No company of our scale and size has ever dedicated itself to this one singular field of computer science. GPU accelerated computing was all we do. Now, as a company of 12,000 people, we've now dedicated and invested some close to $30 billion in the pursuit of advancing GPU accelerated computing.
Easily observable by NVIDIA's stock price, GPU computing is a new industry standard and is now being massively adopted across all fields that require intensive computing. This is also observable by the trend of compute performance over the past 120 years, with the last 7 data points from 2006 all being GPUs. The majority of GPUs are still primarily at 16nm node sizes, able to deliver performance at teraflop levels, such as NVIDIA's Pascal and AMD's Vega high-end consumer cards, which both clock in around 12 teraflops. This is just the general performance for calculations run on these GPUs. As discussed in a previous video in this computing series, hardware and software optimizations can increase this performance much further. This can be exemplified by NVIDIA's latest GPU architecture, Volta, specifically designed for artificial intelligence. Their highest-end card, the Tesla V100, boasts a core count of 5,120 with a node size of 12 nanometers, yielding general performance of 15 teraflops. However, when running machine learning computational tasks, yields a performance of 120 teraflops, 8 times greater than its general performance and well exceeding the prediction of Moore's law. This insane performance is achieved due to tensor cores and tensor sort. As mentioned earlier, deep learning involves many matrix operations. Tensor cores are specialized hardware on Volta GPUs that allow for asynchronous computation for the multiplications and additions involved in these matrix operations. This yields 12 times greater throughput than the same operations on a Pascal card. Tensor sort, simply referred to as TensorRT, is an optimized compiler for machine learning code. So essentially, NVIDIA Volta cards support various machine learning languages such as TensorFlow, PyTorch, and others. Then TensorRT compiles and optimizes the code to be run on the tensor cores. This is done through various processes such as reduced precision, layer fusion, multi-stream execution, and much more that we'll explore in a future AI video. This optimization yields 40 times boosts in performance and 30 times boosts in efficiency, and this design methodology is a pinnacle of hardware and software optimization, and how 1 to the 14 flop performance is achieved for these machine learning computations. In terms of practical applications for machine learning models, a 40 times boost in image recognition and a 140 times boost in natural language processing is seen, as well as a halved latency for both. This is a huge deal. When talking to a virtual assistant, for example, 0.3 of a second versus 1/10 of a second make a vast difference in the experience. It is also worth noting this is just the first iteration of Volta architecture. The Tesla V100 is a data center chip and only buyable in a DJX unit. This is quite expensive, in the range of $70,000, but its purpose isn't for an average consumer and mainly made for startups and other such companies. As of recently, December 2017, the Titan V was announced. This card is the first foray into consumer-level machine learning with a price tag of $3,000. As time progresses, industry cards like the V100 and consumer cards will only get better and cheaper, opening up AI for everyone. In terms of general GPU computing, also referred to as GPU computing, there are various optimizations both in hardware and software being made. GPUs have built-in memory called VRAM, which is essentially like DRAM. New GPU memory architectures are reducing the latency caused to memory induce. This is called HBM, high bandwidth memory, and like 3D NAND utilizes more Z-space, which allows for more memory to be added to GPUs, as well as bringing the memory closer to the processing die to reduce latency. Also, evolving PCIe standards with 4.0 and 5.0 will also assist with data bandwidth and GPU power consumption. If you want to learn more about memory and data, be sure to watch the previous video in this series if you haven't already. In terms of software optimization, NVIDIA's Compute Unified Device Architecture, CUDA platform is beginning to grow massively. CUDA is essentially a parallel computing platform which allows developers to utilize the mass parallelism in GPUs for general purpose computing. There is also improvement in the graphics and simulation front with DirectX 12 and Vulkan APIs. These allow better GPU multithreading, CPU communication, and much more when it comes to gaming and other simulation and graphically intensive tasks. All in all, GPUs are just beginning to hit their prime, with more adoption and exponentially increasing performance due to major innovations in both hardware and software. And they still have a long ways to scale, with general performance expected to continue growing into the 2040s. Performance is currently growing at a rate of 10 times every 5 years, so following that logic, by 2040 we'll have GPUs 100,000 times better than today.
So there you have it, a tour through GPUs. You should be aware that laptops do not have high-end GPUs. If you want a game, you really have to be on a desktop to get the advantage of the massive speeds that the current GPUs offer in gaming. If you like this post, don't forget to subscribe, and I will see you next time.